boys and girls. Now notice in this chapter we're dealing with a quadratic function, and then in fact we're going to go on into a polynomial function, a more general case than a quadratic. But right now what we'd like to do is to take a little bit of a detour, if I may use that word, in order to be able to get more background of numbers, and in fact the name of the lesson has to do with imaginary numbers. Now, let's look at an example of an equation such as x squared is equal to 1, in which our domain for the number x is then over the set of real numbers. And we look at x squared is equal to 1, and of course the solution set for this sentence we all know is, Doug?
1 and negative
1 and negative 1. And indeed there's no problem. Now, if we were to change the example to x squared is equal to negative 1, and x is still over the set of real numbers, if we ask the same question, what's the solution set of x squared is equal to negative 1, what must we conclude on?
null set.
But that it is the empty set. Now, we could go on through life having only this set of real numbers and coming to the conclusion that the solution to this equation is indeed going to be the null set. But at some time or another, I think what you'd like to do is to say, I wonder if there is some number which I can make which will satisfy this sentence. And what I'd like to do, and in mathematics, every time you get stuck, what you do is you make a definition. All right? So let's make a definition for a number which I'm going to call I, in which I'm going to define I squared to be negative 1, in which I may then also say that I then is going to be equal to, and let's take then the positive square root of this number, negative 1. Okay? Now, from this definition, let's look then again at this equation of x squared is equal to negative 1. And from what we have been saying thus far, and if we would like to have all of the properties and all of the theorems and the rules that we've been dealing with thus far over the set of real numbers still hold true for this other set of numbers which we haven't yet given a name, what then would be the solution set of this sentence? Looking at it, well, x then is going to be equal to, and what numbers? If we have x squared is equal to a, we said that x must be equal to what? The positive square root of a, which in this case is going to be what? The positive square root of
Negative 1.
Of negative 1, or x then is going to be what? The negative square root of negative 1. But we've just given a name to the square root of negative 1, which is what? Which is I. Therefore, x is equal to I, or x is equal to what? The opposite of I, which in fact we may call negative I. Okay? Now, then, if we were to write this in terms of our solution set, we have the two elements of I, comma, negative I, would then be the solution set of the sentence x squared is equal to negative 1. Well, here we have the square root of negative 1. I think perhaps it's worthwhile asking ourselves the question, can we take the square root of other kinds of numbers? For example, what do we mean by the square root of negative 4? And just looking at it, is there anyone who can then give me a number which you think is going to be the square root of negative 4? And I want some number which, when multiplied by itself, is going to be negative 4. Brenda?
2i.
How about the number 2i? Because 2i, the quantity squared, is going to be what? This is 2 squared times I squared. Again, we would like to have all of the properties of real numbers hold true. And 2 squared we know is 4, and I squared is negative 1, and 4 times negative 1 is negative 4. How about the square root of negative 9? And you would like to say then, Charles?
3i.
This is 3i because 3i all squared must be negative 9. How about the square root of, say, the opposite of b squared? And the square root of the opposite of b squared then is going to be equal to, Dick?
Bi.
Pardon me?
Bi.
b times I, because bi all squared is going to be equal to what? But the opposite of b squared. Now this number bi here is given a special name in which we call this a pure imaginary number, okay? A pure imaginary. Now, in fact, I think that gets us ready for the definition of what we would like to say. And suppose, well, let's say if r is greater than 0 and r belongs to the set of real numbers, then the square root of the opposite of r is going to be equal to, and what do you think we would like to define this to be equal to? And this then will get us over some other set of numbers here. Glenn?
Square root of r.
the square root of r times I. All right? Now notice here we said that r is greater than 0. And in fact, we may even make another definition in which we have r is equal to 0. All right? If r is 0, the square root of 0 we know is 0. And then we have 0 times I. And what do you think you'd like to define 0 times I to be equal to? And you'd like to say that this is 0. And now notice this is a definition. The reason we select that as the name for 0 times I is, again, that it's going to be consistent with everything that we have done in the set of real numbers. Well, let's look at some other examples and ask ourselves, do the properties of, for example, associativity and commutativity and what have you hold true when we're dealing with these pure imaginary numbers? In other words, 2 times 3i you would like to say is equal to, and well, using your associative property, you'll have 2 times 3, and then it's that number times I, and of course the most simple name here is what? Done? 6i. Is 6i. How about negative 2 times 3i? What can we say about this? This will be equal to, Malcolm? Negative 6i. Well, how about 2i times 3i? And what then would you like this product to be? And again, you can use associativity, commutativity, and what have you with respect to the set of real numbers. But in the final analysis done, you'd like to say
6i squared.
this is equal to 6i squared. Good. But what then is I squared equal to, Steve?
Negative 1.
Negative 1. Therefore, it is what?
Negative 6.
Negative 6. Okay? And let's see now. Suppose let's take a negative 2i times 3i. What do you think this would be equal to? And Doug?
6.
This is then simply the number 6. Does everyone agree with that? Because it's then going to be a negative, or the opposite of a negative 6, which is 6. Oh, how about negative 2i times a negative 3i? And what then would you like this number to be equal to? And Brenda? It's then going to be the number negative 6. And I think if you will, here we have I times I is I squared, which is negative 1 times a negative 2 times a negative 3, I think we'll agree is a negative 6. Well, let's see now. Perhaps there are 1 or 2 other ideas that we can look at here. So let's look at powers of this number I. I to the 1 power we would like to say is equal to simply what? Is I. And I squared we have already said is equal to what? Negative 1. What can we say about I cubed? Now that's I squared times I, isn't it? We would like to have that property hold true, which is going to be what, Brenda? The opposite of I. How about I to the 4th power? That you would like to say is I squared, all squared, and I squared is negative 1, and negative 1 squared is 1. Everyone agree with that? Now, how about I to the 5th power? And now notice here, I to the 5th is I to the 4th times I. I to the 4th is 1, so it's going to be 1 times I, which is simply what? This is I. What do you think I to the 6th power is going to be? Negative 1. I to the 7th power? Negative 5. I to the 8th power? 1. And in fact, I think you see a pattern developing. What then would be, say, I to the 18th power? And you look at 18 and you say, let's see now, some multiple of 4 plus 2, which is going to be what? I squared, isn't it? It's 1 times I squared, which is negative 1. Oh, how about, say, I to the 101st power? Is that right? Is it negative 1? I to the 18th is I to the 16th plus 2. Is that right? Which is I to the 16th is the name for what number? Is the name for 1 times I squared, which is negative 1. How about I to the 101st power? What can you say about that? And I think you will agree that it is a name for I. Is that right? Everyone agree with that? And I would rather not generalize this, but I think you can think of it as a number which is a multiple of 4 plus some remainder. And it's that remainder which is then going to be one of these numbers, I, negative 1, opposite of I, and 1. Is that right? In which there is this cyclic idea coming out of that. Well, let's look at another situation. And, in our real numbers, if we had, say, the number 1/2 times 2, we know that this is equal to what? Is equal to 1. Suppose I were to take the number I times a negative I. And what then is I times negative I equal to? And it's equal to, Doug?
1.
It's equal to 1. Now, when we have 1/2 times 2, and which then the product is 1, what then do we call those two numbers? They are called reciprocals. And now let's extend the same idea. Since here we have the product of these two numbers is equal to 1, what holds true about I and negative I? They are called what? Reciprocals. So let's include that word in which these are reciprocals. If they are reciprocals, therefore, what is 1 over I equal to? 1 over I must be what number?
Negative I.
Negative I. And in fact, 1 over negative I must be what number?
I.
Must be I. Okay. Well, I think perhaps there's one other big idea that we can look at, and that is to look at a number of examples. So let's look at, say, the square root of negative 9 plus the square root of a negative 25, and see if we can't now add or subtract or multiply and divide some of these pure imaginary numbers. Well, it's another name for the square root of negative 9, Peter?
3i.
Is 3i plus
5i.
5i, and I think you would like to say that this is equal to
8i.
8i. Again, if you thought of your distributive property, which is 3 plus 5 times I, that then is going to be 8i. Let's look at another example. Well, suppose we had something such as 4 times the square root of a negative 24 minus 2 times the square root of a negative 54. And now let's see now. We're looking for a perfect square in there. The square root of 24 is what? That may be thought of as what? 4 times 6. The square root of 4 is 2. 4 times 2 is 8. The square root of a negative 1 is in there, which is a name for what? I. And we have left what? Square root of 6. And here we have a minus. And now the square root of 50 of a negative 54. 54 is another name for what? Of what? 9 times 6. The square root of 9 is 3 times 2 is 6. We have there what? A 6i times the square root of 6. And again, we're right back to the example as we have here in number 1. 8i times the square root of 6 minus 6i times the square root of 6. We have some like terms in there. Therefore, the most simple name is, Tim?
2i times the square root of 6.
2i times the square root of 6. Notice now, by the way in which I have written this is 2i times the square root of 6. We perhaps would rather write 2 times the square root of 6 times I, using a commutative property there. But again, if one gets a little sloppy with that square root symbol, you might have a tendency to put the I under the radical, and therefore I certainly prefer to write it as simply 2i times the square root of 6. Suit yourself whether we write it this way or this way, as long as you know exactly what it is. Well, let's look at a third example, and in fact, this example is quite an important one because it points out a certain idea. Here we have the square root of a negative 8 times the square root of a negative 18. Now, what we would like to do is to look at the square root of negative 8 and come up with the most simple name for it, which is going to be what? Peter?
2i read 2.
This is going to be 2i times the square root of 2 times, all right, the square root of a negative 18. And the most simple name for that is what, Tom?
3i rad 3.
3i times the square root of 2, I believe. Is that right? This is 9 times 2, which is 18. Now, looking at this and using our commutative and associative properties and what have you, 2 times 3 is 6. Root 2 times root 2 is 2. 6 times 2 is 12i squared, which is negative 12. Now, notice here that the name for this is negative 12. Now, what I'd like to do is to point out the fact that the square root of negative 8 times the square root of a negative 18 is not equal to the square root of a negative 8 times the square root of a negative 18. Because when we went through this theorem of the square root of a times the square root of b is equal to the square root of a times b, this theorem was true if and only if what is true about root a and root b? They were, Doug, real numbers. If and only if the square root of a and the square root of b belong to the set of real numbers. So, here is an example which illustrates this very important idea. What you want to do then is to treat this in terms of the number that involves I. rather than trying to multiply it out as we see here, because in fact this is not the case, because the square root of a negative 8 is not a real number, as the square root of negative 18 is not a real number, okay? So keep that in mind as you go through some of these examples. Well, let's do a last problem here. Suppose we had 4 divided by the square root of a negative 2. And again, the square root of negative 2 may be thought of as what? I times square root of 2. Now, we've already said what a name for 1 over I is. What's 1 over I? That's going to be a reciprocal, which is what number? The opposite of I, or negative I. Let's include that number, and then we still have 4 divided by the square root of 2. Now, give me another name for the number 1 that we may have here, another to rationalize, Don.
Square root of 2 over the square root of 2.
Square root of 2, which of course, root 2 times root 2 is 2. 4 over 2 is 2. And here we have a negative 2i times the square root of 2 then, would be the most simple name for 4 divided by the square root of negative 2. Okay? Well, let me give you your homework assignment, and you can practice on some of these problems. This will be